AS Quantum Physics 4, electron waves. We'll be looking at electron diffraction and the double slit experiment. Now, before we do, this is an electron gun and it produces very fast moving electrons. What's happening at the filament is something called thermionic emission, which we'll need to know about later on in the upper sixth. Basically, you get a filament, it gets very, very hot, electrons dancing on its surface. You have an anode, which is very positive. The electrons are pulled off the filament, they gain kinetic energy, and you produce very fast moving electrons, a cathode ray. Now, we can fire this cathode ray at a graphite target. Now, graphite is layers of carbon atoms, this hexagonal pattern of carbon atoms, lots and lots of little crystals. And what happens is it behaves like a diffraction grating, and we get a pattern, as you would with a diffraction grating. We get maxima at certain angles. A pattern of rings is seen. And if we turn up the accelerating voltage, then the rings get smaller. What's going on? Well, now the graphite crystals are acting like a diffraction grating. The electrons are behaving like waves. We are getting a diffraction pattern produced. And we can actually work out the wavelength of the electrons using n lambda equals d sine theta. And why does the pattern get smaller when we turn up the voltage? When the electrons are moving faster, their wavelength is smaller. A very important equation in quantum physics is called the Debry Equation. De Broglie, it's pronounced Debry, and it's lambda equals h over p. H we know is Planck's constant. P is the momentum of the electrons, and the wavelength of the electrons is inversely proportional to their momentum. We use the symbol P for momentum. I could write mv, but usually it's written as P. Are electrons waves or particles? Well, I think of them as particles, but there are some things about them which you can only explain if you say that they have a wavelength. Basically, there's this phrase, wave-particle duality. Is it a wave? Is it a particle? It behaves like both. It depends how you look at it. You know, electrons, fast-moving electrons have a wavelength. Here's a question for you to have a go at. An electron is accelerated using a PD of 300 volts. Ignoring relativistic effects, calculate its momentum and its wavelength. 3, 2, 1. A little bit tricky this. I mean, what we can do is work out the gain in kinetic energy in joules. Then, as kinetic energy is a half mv squared, the way to do it is you work out the velocity and then multiply by the mass of the electron and you get the momentum. And then if you know the momentum using the Debry equation, you can get the wavelength. 7.1 times 10 to the minus 11 meters. Here's another situation where electrons behave like waves, and it's our double slit experiment. What would happen if we fired electrons through a pair of slits? Do we get an interference pattern as we would with, let's say, a laser through two slits? And the answer is that yes, we do. We build up over time as the electrons arrive on the screen, we build up an interference pattern over time. There are places where lots and lots of electrons arrive, and there are places where not very many electrons arrive. Very, very interestingly, if we fire one electron at a time, we still get the same pattern eventually. It takes a while to build up, but this shows that the electrons aren't interfering with each other. Okay? The probability of them arriving at a particular place can be determined using the wave function. In other words, there is a probability for every particular point on the screen, there's a probability that they will arrive there. And to work out what that probability is, we use this wavelength, the wavelength of the electron.